the mixer, so that if you look here, for example, this is just basically a snapshot of the mixer performance with different digital words, just to see that the thing works. But then when we built I want to show you here the mixer. When we started changing the temperature and the supply, as you can see here, you can see all these red parts here that shows you that the performance is not reached. But then when you basically invoke the calibration, then all these red areas disappear. Most of them disappear. Okay? So and that's done under severe variations in temperature and supply, and also variations of the corners. And that's basically a way to test the validity of the calibration that we have. A very important aspect, of course, of this is the overhead. How much overhead, or how much extra circuits you have to add. And here you can just see that the detector, or the sensor, is just a small part of the LNA, a very small part of the LNA. The same thing for the mixer. And here we have the switches, and these are different types of the sensors, that we have just to test some of these new sensors that I mentioned earlier. So, and the way we test that in the lab is that you have the radio chip under test, and you have an FPGA where you have the digital downloaded into it, and you have just a computer to control it. So in an academic or a university environment, it could be a very simple setup to test this thing. So in conclusion, we showed you how to develop a methodology where you can actually incorporate built-in self-test as well as calibration of the RF, most critical parts of the RF. We actually have done that also with the PLL and BCO. I just showed you here the calibration for the LNA and the mixer. And we're now looking into millimeter wave, 60 gigahertz as well, because in order for these things to be manufacturable in high volume, you have to incorporate some kind of built-in self-test and calibration into it as well. We have actually 3 PhDs working in those areas right now into how to, and that requires significant amount of modeling the interconnects, modeling the devices, passive and active devices, in order to be able to see, and particularly nano-meter technology, how can we incorporate these modeling into the design process. And just wanted to, at the end, again, thank everyone here, thank the Semiconductor Research Corporation, the Swedish Strategic Research Foundation, Intel, and these students that I list here that have done many of this work. Thank you very much. Speak a little bit about the, I think maybe some of that will be in the panel also. We are very interested in getting students to work or do research, master and PhD research. We can actually apply online for that. And you have to take the GRE, graduate record exam, and you have to get the TOEFL exam. These are 2 important requirements. And we're looking for students, of course, to join in the US or in Sweden, in fact. So if you want to come to Sweden also, they require the GRE and the TOEFL. They have the same kind of process like the United States. The master degree takes about 15 months, and you can do it with a thesis or without a thesis. So it can be done either way. And the PhD takes between 3 to 3.5 years at Ohio State. Maybe in Sweden it takes a bit longer, about 4 years or so to do a PhD. So if you have any questions about that as well, if you have a question about the lecture, of course you can ask, but if you also have a question about how to apply or what the requirements are, you can also ask questions.
شكرا لحضرتك، كانت برزنتيشن رائعة دي. بس كان عندي سؤالين. في الجزء بتاع السيلف تيست والكاليبريشن، احنا بنحط جزء ديجيتال جوه الار اف اي سي، فالجزء الديجيتال احنا طبعا بيبروديوس نويز عالي، فانا بحط جزء بيبروديوس نويز عاليه عشان يعالج النويز الموجوده اساسا في الاي سي، فازاي عرفتوا؟
That's an excellent question. I mean, that's the question basically is if you have this high-speed digital clocking, how do you put that next to an RF, and isn't that going to affect the RF in a very bad way? Because the answer, of course, is yes, it will, and then there are ways that you can minimize, almost eliminate that completely, and that's usually done at the layout phase. So you do grounding and supply strategy. So you use different supply lines, VDD and VSS for RF that's separate from the digital. You make sure that you have a separation between them, and there's actually the engineers that have experience, they know exactly how much separation on chip that's filled with metal, and that metal is connected to ground, so that if you have any clocking or any noise coming, it will basically make it back to ground. So there's actually many different lines of defense to allow the digital not to go to the RF for the mixed signal. So you also isolate the sensitive nodes in the analog and the RF. You surround those by what we call quiet bias, or areas that are connected to the substrate, so that anything tries to make it inside the RF or the analog is basically bypassed to ground.
السؤال الثاني، هل ممكن حضرتك تفتح شركة في مصر فرع تاني فيرست كلاس في مصر؟
Yeah, actually we have a branch in Egypt, in Cairo, and it's run by a professor at the Cairo University. But we had a lot of people, we tried to outsource some of the work we actually did that, to outsource some of the work to a company called SysDsoft in Cairo. But right now the situation in the US and Europe is kind of slow right now, so we have to cut down this operation in Cairo, but hopefully next year maybe we can set up something here in Zambia.
Thank you, Dr.
أنا سؤالي بس كان من منطلق إن أنا لسه أولى كهرباء، ومعظم الناس اللي كانوا موجودين هنا برضه أولى كهرباء، فأعتقد إن هم بيشاركوني نفس السؤال. يعني هو اللي أنا فهمته من السيشن هو كان إزاي إحنا ممكن نقدر نخلي الحاجة تشتغل من أول مرة، فعشان التكلفة بتبقى عالية والدورة اللي هي بتاعت 9 شهور دي، بس هي بقية السيشن بالنسبة لي كانت معضلة. ده كان سؤال. السؤال الثاني أنا كنت عايز أعرف اللي هو بالنسبة للواي ماكس في مصر إيه نظام؟
أوكي. أنا نفسي بس تعيد السؤال الأولاني one more time if you don't mind.
يعني هو أنا فهمت ممكن الأوت لاين بتاع السيشن، بس يعني من جوه السيشن بالنسبة لي كانت مشكلة يعني.
أوكي. يمكن maybe I was going so fast, but it's basically a very simple loop. يعني feedback loop. Excuse my Arabic is not so good يعني ممكن أتكلم بالعربي إن أنت تعمل feedback loop دي first to do يعني built-in self test، تعمل تيست للفينومينا مثلا noise figure أو linearity or gain، وبعدين تاخد التست result تقارنها some lookup table, and that lookup table in the digital domain tells you what the result should be in an ideal situation. فلو الريزلت بتاعت التست is far from the ideal, there is an algorithm يعني في زي ما تقول program or some algorithm بيقلل ده least square mean least square or something like that you can invoke. It's a mathematical thing that you can actually minimize the distance between the test that you have now and the actual or the ideal test. And then you have a signal that goes in the feedback loop to correct the performance of the. So it's a very simple feedback loop actually that you can use. So I can maybe show you quickly here. For example, this one. So this mixer here, for example, I don't know if you're familiar with this type of radio, but it doesn't matter, you don't have to be familiar with that. But this mixer here, you sense the input, so you sense it, and you sense the output here. And then here you have some kind of an algorithm that compares the result of this mixer here with something that you have inside the digital that tells you what the performance of that mixer should be.